So we are going to wrap our sampling procedure as a function, right? So we are going to be returning a probability is equal to samples. Okay. Essentially, we are going to be turning this whole thing into a function. And we're going to perform this function many times. So we are going to say probabilities is equal to an empty array. And let's perform this thing 1,000 times. Probabilities is equal to probabilities samples. Okay, so as you can see, we are basically computing the probabilities again and again, and every time we compute it, it's going to be a different value, right? And I hope the 1,000 times is going to complete pretty soon. And then we are going to be plotting the histogram of the computed, the 1,000 computed probabilities. Okay, so these probabilities is going to be having 1,000 numbers, and of course they are all different. So let's close and plot the histogram of the probabilities. Let's use maybe 25 bins. So that is what we get. Okay, so essentially we see a shape that's a little bit like what distribution. It's definitely not uniform, right? And the distribution seems to be a little bit high in the middle and a little bit low at the two ends. Okay, so of course we have only 1,000 samples, so we don't actually, we only get a pretty noisy version of the distribution. And let's see if we increase the number of samples, how does it look like? And in order to make it faster, I think the best thing I can do is to disable the plots. And we're also going to put suppress the output. Okay, so then let's do this many more times again. Let's do this 10,000 times again. We do this. Okay, so now we have 11,000 copies or samples of the probabilities. And now I plot the histogram again. Is it the same thing I got? Oh, okay. Interesting. So this increasing the number of samples by 10 times doesn't seem to change the distribution that much, right? Let's see if I do this whole thing again. Story. Increase this by another order of magnitude. How does this look like? And I'm going to be plotting the histogram again. Okay, yeah. So now we see the seemingly gaps has been filled out a little bit. So here we see we can get a wide range of outputs, all the way from very close to 0 to almost a 3% probability, right? That what that means? That means that if we were only able to run the simulation for one time, I mean, if we are only able to sample and compute the probability just for one time without looping through and computing the probability again and again, we actually get a pretty uncertain result, right? So let's say we perform a sample and we are so lucky that we get a number that's very close to 0. We shouldn't just assert that the probability that we crash is very close to 0. Because in fact, if you sample this a lot more times, you're going to get some much larger values, you're going to get like 2% or more. So how can we put a estimate of uncertainty in our Monte Carlo result? How can we have a confidence interval, right? So the idea is instead of producing a single number, let's say the probability of crashing is equal to 1% or 1.7%. How about putting an interval around the result we produce? So let's say in this case, it might be appropriate to say that the probability of crashing is between 0% and 3%, right? That is going to give any decision that has to be made based on this Monte Carlo simulation a lot more informative than just giving a single number, let's say 1%, without knowing how uncertain this 1% number is. Okay, so that's something we're going to be talking about in our next lecture. That is, how do we put a confidence interval around our Monte Carlo result? Or how do we estimate the uncertainty in the result computed using Monte Carlo methods? All right, so I will see you on Wednesday. And any questions on what we discussed so far? No? Okay, so I guess I will see you on Wednesday, and stay safe. Okay, bye.
Thank you.
Mm-hmm.
Thanks.
Yeah.
Chi.
Bye.